Hi guys, what's up? How's it going? Give me a few minutes. How's everyone doing? All right. Now my class isn't here today. That's what I'm dealing with. How do I hope they see my message. Just waiting for them. Okay, let's start. Hopefully they'll get here. Should I keep this open? I shall keep this open in case a message. I hate this. Okay. All right. We can start now. Hello, Messam. You're not on Zoom? Someone get on Zoom. I'm lonely. Okay, let's start. Okay, we're doing May, June 2020, the paper that got cancelled because of Corona. We'll do most of the questions. We'll skip one. I think it's question number 3. Skipping that. Okay, let's just get right into it. Okay, student investigates a sample of rock salt. The student grinds the rock salt into a powder, places the powder into a beaker and adds water to it, stirs the mixture, pours the mixture through the apparatus shown. So he's trying to filter it. Okay, name A and name B. What do you guys think? By the way, Masim, there's a new link. Check the chat on Mighty Networks. Hello, Abdul Ghani. Guys, there's a new chat, new link on Mighty Networks. I sent it in chat. You're using that today. Use that to join. Okay. Okay. I had decided some colors. Okay. The A is, what is it? Well, it's a filter funnel. Filter, my hand hurts already. Filter? Funnel. And B, what is B? It's a conical flask. Conical flask. Okay. Brown solid remains in the apparatus A. A colorless solution is collected in apparatus B. Name the process used to separate the solid from the colorless solution. I wonder what it's called. It's called filtration. I mean, why? Okay. The colorless solution contains 2 different cations. One is sodium. Okay. They're not asking about, hey, Miral. Oops. Guys, come on Mighty Network. Why are you guys not on Mighty Network? What's up, Miral? How's it going? I think they can. I don't think... Abdul Ghani, weren't you on Mighty Network? Oh, well. Continuing with the question. A student adds dilute nitric acid and aqueous sodium sulfate to the colorless solution. A white precipitate is formed. Name the other cation in the colorless solution. One thing you want to note is that they're not talking about sodium. So they're only testing for one ion. So rephrasing this question is just that there's one cation. There's a cation that forms a precipitate when what is added to it? Student adds dilute nitric when sodium sulfate and dilute nitric acid are added to it. So yeah, SO42 minus. Now this is the kind of thing we don't really, the cation mentioned, we don't really test for it ever, right? It's not even technically in the syllabus, if you can argue that. But if you think really hard for a second, you'll realize that there is a test for sulfate ion. Do you guys know what that test is? The test for sulfate ion is if you add barium chloride solution to sulfate ions, or any solution containing sulfate ions, it'll automatically turn into barium sulfate. So you're doing the opposite, where you're adding sulfate ions and you're seeing a precipitate. So what is the cation present that's giving you that precipitate? It has to be barium sulfate. Oh, sorry. Because this precipitate is barium sulfate, but the ion is barium 2+. I hope this makes sense. This is probably the Kurosaki. It's on the website. It's only for people who've joined Mighty Network. They know where it is. It's okay. I was just talking to my students who are on with me on Zoom normally. Take it. I hope that made sense. There is a bit of lag. Okay. Let's continue. I wonder if anyone's entered Zoom. No, no one has. Okay. Student investigates the effect of adding different masses. Oh, is the audio is insanely loud, Rania. I don't think should be an audio thing. Can I explain it again? Okay. This cation anion part? Yeah. Okay. Now, there's no real test for barium ion, if you think about it, right? But you're adding the sulfate ion into the solution and you're getting a precipitate. Now, what you're told so far, this is actually like what's going on in this reverse. If you can pick that up, you'll understand it very easily. What's really happening, or what you're told is, if a solution contains sulfate ions, you add barium chloride to it, or just barium ions to it. And what happens is barium sulfate is formed, which is a solid, and forms a precipitate, a white precipitate. Okay, this is what you know. This information is in the books, right? Sulfate ion ka test, add barium, aqueous barium ions, right? Now, over here, what's happening is the reverse. You're adding sulfate ions and they're saying a precipitate is formed. A white precipitate is formed. So what forms a precipitate that you know of when you throw sulfate ion in there? Well, the only thing that comes to mind is barium. So barium must be in the solution, right? So normally what they ask the question is that you add, like normally what you'll see is barium is added to a solution and a precipitate is formed. What is the anion present? And you say, oh, it's the sulfate ion, right? This time around, they've given you the sulfate ion, knowing fully well, okay, it's only the barium ion it reacts with to form the precipitate, right? I hope that makes sense, but I'll move on now. But if you don't get it, give it some time. This is, I think, a very tricky question, a little early in the paper. Let's just do some salt analysis questions. Then we can probably look into this and it should look easier then. Moving on now. Okay, this is straightforward. The diagram shows the volume of water the student is investigating. And state the volume of water the student uses. The water height is 15 is over here, and this has to be 16, so it's just 16, right? Miral, there's a different link I shared in the chat, so if you can look at the chat, you can join there. But if you can't, I think this is fine as well. Okay. The student places the water in a beaker, adds ice to it. This goes to an interesting part. Stirs the mixture, measures the lowest temperature of the mixture, repeats the experiment 4 times. In each of the repeated experiments, a different mass of rock salt is added to the mixture. State a variable that needs to be kept constant in this experiment. So what's happening is, I think the rock salt dissolving in water is an endothermic or an exothermic reaction, right? And when you add rock salt to it, the temperature changes. So first he cools it down to 0 degrees, because I've read the question, he cools it down to 0 degrees, then adds salt to it and measures the change in temperature. So that's what he's doing. So what variable does he need to keep constant? Well, the amount of water he's using, right? That needs to be constant. If you use too much water and the water heats up because of the reaction, well, because you can only measure the heat by the change in temperature. If it's too much water, the same amount of heat might not change the temperature by a lot. Kind of like, when you have an entire saucepan full of water and on a stove for 5 minutes, it'll heat up by let's say 5 degrees. But if you have a tiny half a glass of water on the stove for 5 minutes, that tiny water in the same amount of heat will boil, right? So that's the difference. So he needs to make sure the amount of water is constant. Amount of water is constant. Now anything else that comes to mind is also valid. So let's take a look at what else he's doing. Okay. He's adding ice. Now ice will eventually melt, and that's also water, right? So he has to keep the mass of ice a constant as well. He should put the same amount of ice in the water. Mass of ice he needs to control. Anything else coming to mind for this? Yeah, Rania already said it. Amount of ice too. I actually like that way more than amount of water. That's my first choice. But only to explain amount of ice, I said amount of water first because, ice is water. Okay. Pressure, you're not controlling pressure. Nothing you're going to do will change the pressure. Because it's an open beaker. You're not changing the pressure. It's just like you're adding powder to water. It's some, I hope that makes sense, okay? Moving on. The diagram shows the part of the thermometer the student uses to measure the lowest temperature reached when 1 gram of rock salt is added. Okay, so we have to record this temperature. Now if I take a closer look, 3, 4, and this looks like a graduation of 10, I'm pretty sure, and this is negative 3.9. So this value is going to be negative 3.9, right? Moving on. Oh no. Okay. 0, 0. Okay, let's try it. What's a good color here? Let's go with orange. 0, 0. 0.5. I have to graduate it. What's our range? Okay, yeah, so our range is, it's starting from 0 going to 2. And if I go here, the temperature is marked, but I need to mark this area. So I'll graduate it accordingly. This is 0.5, this is 1.0, this is 1.5, and this is 2.0. Now I won't be exceeding 2.0, so this is a fair distribution, right? Could it be more ideal? Okay, let's look at the second. At 0.5, the temperature is negative 1.9. I have to find negative 1.9 here. So this is my line for 0.5, and negative 1.9 is going to be, how much is each graduation right now? Pretty sure that's 0.2 degrees. So 0.8 will be here, 0.9 will be at the middle of these 2 points, right? So I mark that to the best of my ability right in the center, right? Then I have to look at 1.0. It's minus 1.9. No, minus 3.9. Minus 3.9 is going to have a similar, right before. What's at 1.5? Minus 5.8. and that's going to be on this intersection, minus 5.8. I hope you guys are understanding this. I think graphs, right? Like, I don't think we should be discussing graphs. 5.8, 7.8, sorry. I said 5.8, it was 7.8. Take care. Does this make sense? I think you guys will have a decent amount of difficulty seeing this, but let me draw a line. Let's see if that helps. Let's get a nice color. 1, 2, 3. No, that doesn't work. Doesn't work. Not bad. I'll settle with this. Not bad, not the worst line. Okay. Use your graph to find the lowest temperature when 1.4 grams of rock salt is added. 1.4, where will that be? I think 1.4 is going to be here exactly. Why do I say that? Because 2 of these squares is a 0.1 equal to 0.1 grams. And that's 0.1, that's 0.2, that's 0.3, that is 0.4 where the question's asking, and that's 0.5, so it makes sense. I go all the way here, tracing this line, it's coming over here, and it's over here. So I'll mark that, right? And I'll also highlight this point for reference, kind of like that, or maybe green is fine. What is this value? It's minus 5.4, I think. So let's write down minus 0.4, minus 5.4 degrees Celsius. Use the graph to find the lowest temperature when 1.4 grams of rock salt is added. Should be minus 0.4. Let me just have a quick look if I'm making anything. Yeah, I think it looks fine. Minus 0.4. The line's pretty straight. If the answer is different, I think I didn't draw the line exactly. I think all these points are in one line, and you can use a scale to very easily draw the line. Okay, straightforward. Deduce the relationship between the mass of rock salt added and the lowest temperature. What happens to the lowest temperature as, you know, the mass of rock salt? This is more of a math question. Like, not really a math question, but it's better expressed if this was a math question, if you guys understand what I'm trying to say. But oh well. So what you're going to say is, as you increase the mass of rock salt being added to the solution, the temperature, the lowest temperature is decreasing, and that's what you'll highlight, because it's the exact observation they're asking for. So increasing, let's get a different color. Increasing the mass of rock salt decreases the lowest temperature. No, I think the phrasing isn't right. Increasing the mass of rock salt decreases the lowest temperature. No, I'm not. I think just lowest temperature is just making it tricky. I'll just say decreases the temperature because it just, you know, feels right. Decreases the temperature. Or lowest temperature, it's fine. It just doesn't sound right when you say it like that. Okay. Any questions so far? Please ask. I'll move on. But if I see a good question, inverse relationship in the statement, like how? Decreasing the temperature, you mean? Or in decreasing the mass? Yes, you can. You can say decreasing the mass of rock salt increases the temperature, I guess. Lowest temperature attained. But I wouldn't advise it. Right? Why? Because it's the wrong thing, the wrong way to look at the same problem, even though it's not. Lowest temperature decreases with increasing mass? No. You can't say that, Khatija, and the answer is very, very good. in an experiment, you do something and you measure something, right? You're doing something and you're measuring something. Over here, you're doing, your work done is the mass. Like that's the thing you're doing, you're controlling. You're changing that, and the result of that is the temperature changing, right? Never will you say like, oh, what is the mass if I keep the temperature at -5 degrees, right? Because you can't bring the temperature. It's not in your control. But what is in your control is amount of mass put in and the result of that mass, which is the temperature, right? So it's never the other way around for this case, especially for this case. But always go with, you know, compare it with what you're controlling. What is the, I'm changing this and the result is changing this way, if this makes sense. I think it makes sense. But if you have more questions, ask. Question number 2. Lime water is saturated, I think we have a titration question. Lime water is saturated solution of calcium hydroxide. Okay, we knew that. A student finds the mass of calcium hydroxide in 1 decimeter cube. Okay, let's read this carefully. The student measures 25 centimeter cube of lime water into a flask using a 100 centimeter measuring cylinder. Measures the 25 centimeter of lime water into a flask using a, that's really odd. Do you guys think, do you guys know what's wrong here? Oh well. Adds a few drops of methyl orange indicator to the flask. That's nothing new. Places 0.1 mole per decimeter cube of hydrochloric acid in a burette and takes the initial reading. So he has a flask with lime water and the indicator. The solution is at 25 centimeter cube volume and the burette has hydrochloric acid, you know. Sorry for my poor drawing. And he titrates it. Okay, I have to record the readings. This is good. This is good. Why? The first one is 0. And let's get some fancier colors. The first one is 0. No. The first one is 0. And the second one is 11.6. Total is 11.6. The second one, for the second one, oh, it's 11.6. What a coincidence. And it goes to 23. This is 23, 23.5, 6, and 7. 23.7. Okay, someone do this math. That's 1, that's 2, that's 1. Okay. And what do we have? Okay, then it's still 23.7, yes, of course. 23.7. And it's, what is this, 34.9? 34.9. Am I going too fast? I think this is straightforward, right? 34.9. Yeah, what is this? 0.2. 1 and 1. 11.2. Am I doing this right? Lowest temperature decreases. Am I doing this right? What do you guys think? Okay, the results are not consistent. Identify the apparatus the student used that is not accurate enough for the titration. So he performed a titration experiment, and at one point he did, at a very early point, he did something really weird. He used measuring cylinder to measure 25 centimeter cube. Why is that a bad idea? The measuring cylinder. The measuring cylinder will allow you to measure 25 centimeter cube, but it won't be as accurate as a pipette. Yes, a pipette should have been used. Pipettes are way more accurate. The only flaw with a pipette is that they can only measure a certain amount exactly. So normally it's 25 centimeter cube, but they're way more accurate than a metric cylinder. ठीक है. A student adds hydrochloric acid drop by at the end point of the titration. Suggest a reason suggest a reason for this. You don't want to go past the end point. So how do I phrase this? Suggest why the hydrochloric acid prevents student from going past the endpoint. Or in other words, how else would you say it? So we can, not mess up our value, and we can determine the exact volume that of the acid used to neutralize the lime water we have. Okay, the results are shown in the table. We have some other results, and we have to tick the best titration result in the table. So whatever two values are the closest, because one would be wrong then. So I think these two are the closest, because 0.6, only if I add 0.2 to it, it'll turn into 11.8. But if I subtract 0.3 from it, it'll turn into 11.3. So these two are closer than the other two. And I'll use pink. Use the values to calculate the average of 0.10. Okay, what's the average of 11.8 and 11.6? I'm gonna go off a limb here and say it's 11.7. But you have to show the calculation, so it's 11.8 plus 11.7. Add them up, divided by the number of things you added. But I'm pretty sure it's 11.7. 1 and 2, 11.7 average. Yeah. How many of you people can just see it and go, oh yeah, that's the average, it's 11.7. And how many have to kind of calculate it? Show me hands of people who have to calculate it versus who can just do it. I just did it, not that I'm good at math. It's just the middle average is normally between two values is just the middle value, right? So the middle value of 0.8 and 0.6 is just 0.7. Calculate the number of moles of HCl in the average volume. Okay. Number of moles, how do we do that? Concentration की बात हो रही है. Moles is equal to concentration times the volume. The volume has to be in decimeter cube. What is this value in decimeter cube? I have to divide it by 1,000. That's going to be 0.0117, I believe. Is it 0.123? Sorry, 1, 2, 3. Is that how it is? Yeah, I think so. 0.017. I have a feeling I'm doing it wrong. Is it? Yeah, I'm right. Never mind. Okay, the concentration is 0.1 mole per decimeter cube, right? And the volume is 0.0117. And that just, divides the entire thing by 10. That's my volume. But I don't like writing my answers in white. 0.00117. Is it necessary to show the working? Yeah, it is the average. Think about it this way. If it's a question with more than 1 mark, and if you get the answer wrong, the examiner can give you marks for the correct working. That's how I see it. So, might as well utilize it. It's always best practice. Okay. Calculate the number of moles of calcium hydroxide. But for 1 mark, I think if you write it, it's completely fine. Calculate the number of moles of calcium hydroxide in 25 centimeter cube of lime water. So this is the amount that was neutralized by these many moles. So it's just in the correct ratio. So let's go back to pink. 0.00117 is the acid. How much is this going to be? The ratio between them is 2:1. So I have to divide this value by 2. And let's do that. Let us do that. Divide this by 2. I got 0.30585. And I'll write this as 5.85 times 10 to the power minus 4, because I like it better that way. Calculate the number of moles in 1 decimeter cube of lime water. So what we did was we figured out the moles in 25 centimeter cube. Now they're asking find it in 1,000 centimeter cubes. Isn't that, tell me if you get this, isn't that 5.85 times 10 to the power minus 4, divide that by 25, then multiply it by 1,000. What get you? Someone check my values. $25 centimeter cube of lime water को consider नहीं करेंगे? What do you mean? Am I doing something wrong? Talat? All good? I feel so exposed. I'll just wait for a second here. Is this okay, Talat? What's your question? I'm not moving ahead because, it's so easy to make a silly mistake, and, I'm not the best. Like, I know what I'm doing, it's just that the question is a little too easy. Sometimes you make a silly mistake. Okay, let's review it before. This is fine, right? That's the average. Use the okay. Calculate the number of moles of HCl in the average volume. And yeah, this is fine. Average volume, right? So this is the moles that titrated all that, what do you call it? Lime water. Calculate the number of moles of, I am suspicious of something. All is good? Talat got it as well? Okay. Just confusing me. Don't scare me like that. I find these questions very confusing, not because, they're calculation intensive or anything. I think they're very easy. It's just that when they divide it into 4 different parts, I'm like, what are you trying to ask? Just give me a 4-mark question and I'll do the titration and I'll give you the right answer. Don't do this to me, like, then later I get, like, if I make one mistake here, then I'm confused, like where I'm at, because these words just feel alien to me when I'm redoing the question. And I think I hit undo. Oh well, let's move on. Calculate the MR. Okay. Calculate the MR, which is 40 plus twice of 16 plus 1. 16 times 2 is 32, so 34 plus 40, which is 74. Mass in 1 decimeter cube of lime water. What is the mass? So what are the moles? These are the moles. These are the moles. So the mass is going to be the moles times the MR. The moles are 0.0234. 0.0234 times the MR, which is 74. Zero 0.0234 times 74, 1.73. ठीक है, easy peasy. Okay. Salt analysis already. 9:37. Okay. Okay. We're skipping a question. Over here there was a question. We're skipping that. And from question 2 we're moving to question 4. Okay. Scientists analyze a sample of soil. They discover that did we go a little too fast? Okay, they discover that the soil contains nitrate ions. Okay. Nitrate ions, carbonate ions, and iron 3 ions. Complete the table to show the observations of their test. Name any gases formed and state the use. Okay, you have to name the gases and test used to identify them. Test on a solid sample of soil. Add aqueous sodium hydroxide, then add aluminum foil and warm gently. That's a test for nitrate ions. And you know what happens there. So you get bubbles of a colorless gas that turns damp litmus blue. I wonder if you're supposed to write this much, because they don't give you that room. And the gas responsible for this is ammonia is given off, and that's the test for nitrate ion. Ammonia is given off and you put aqueous sodium hydroxide with aluminum and warm it gently. And I wonder what happens with the second one. Carbonate, though, you know it, you love it. Who doesn't know what happens with carbonate? Turns lime water milky. Weren't we looking at lime water just a question ago? Oh, carbon dioxide, sorry. Right? Does this make sense? Okay. Now what do you guys think? What is the result when you add aqueous sodium hydroxide? Do the test for iron ions. Who knows a good way of remembering these? Yeah, I think saying red litmus paper is probably better, but sometimes even the marking scheme say just damp litmus paper, blue. Damp is probably more important, but I think they just let it go. If people just say it turns litmus blue, you don't even have to highlight paper. But the correct thing is, because dry litmus paper doesn't do anything. And you can imagine why, because the gas doesn't dissolve. It has to, dissolve in water to be alkaline, and the litmus paper tells you that. So damp litmus paper, gila hota hai. Gas gets absorbed absorbed isn't the best word, but dissolves in the water in the dampness, turns the water alkaline, and the litmus paper turns blue. Anyway, red precipitate is formed. Red precipitate is formed, reddish brown. I love this red. What happens when you add excess sodium hydroxide? Iron, I don't think anything happens to it. No change. Or precipitate doesn't dissolve. Yes. The scientists also want to know the pH of the soil. Oh man, like I hate this question. They shake they're essentially asking what is the color of universal indicator at pH 6, and as if there wasn't enough rectification involved in chemistry. But the answer is yellow. Strictly yellow. Precipitates are insoluble? Okay. Well, that implies all precipitates are insoluble. I'm just joking. Okay. The color of the indicator at pH 6 is yellow. Okay. Oh, that's a big question. Scientists believe that some fertilizer contain iodide ions that have been added to the soil. Describe how the scientists could test for the solution. What's the test for iodide ions? 9:44 already. Time flies when you're trying to dissolve precipitates. Test is what is it? Is it nitric acid? Is it nitric acid? Yeah, I think there is. Add, I'm a little rusty. Add, yeah, nitric acid followed by not ammonia. Add nitric acid followed by silver nitrate. Silver nitrate, I know. Just forget what you use with it. Then add HANO3, and it's like, yeah, awesome. Okay, the result of this is going to be a nice bright yellow precipitate. Well, it's not bright. Yellow precipitate is formed. I think everyone has halides under control. It's just the calcium and the aluminum and zinc, they just like mess with you. Okay. Easy question, I think. This part is easy. Precipitates are inside reddish brown. Yep. Okay. Moving on. I think let's try to finish this question if we can. Leaves of plant contain number of different colored pigments. 4 students want to extract and analyze some of these colored pigments. The leaves are chopped up and ground using mortar and pestle, and then mixed with ethanol. The pigments are separated using paper chromatography. Suggest a reason for cutting and grinding the leaves. What do you guys think? What's the reason for this? What is the reason for this? So all the dye is like within the plant cell. So you mash it up so all that liquid comes out. I like saying, my teacher once told me to say, to break the plant cells. To break the walls of the plant cells. To break the plant cells. What do you guys like saying? 2? Why are we given so many? What do you mean? Why are we given so many one-line answers? Where? Why are we giving it? Why am I giving it? So you won't say colors, you'll say dyes or all the chemicals, fine. Like, why are they asking so many one-line questions? Their paper, their mercy. Okay. 4 students do paper chromatography separation. The diagram shows 4 sets of apparatus used by the students. 3 of the students make the mistake in setting up the apparatus. Okay, so essentially an MCQ. Okay. ठीक है. Which diagram shows the correct setup of the apparatus? Okay, let's take a closer look. If we're taking a closer look, that's the line, that's the ethanol solution, ethanol solution, ethanol solution, ethanol solution, right? And what else is different is they have lids. Can you guys tell me why a lid is probably important over here? For the previous question, Ibrahim, can you guys write, like, if you have a question, please write like full questions. If you're answering me, there is lag, right? Like Ibrahim is saying for the previous question, I don't know which question, that could be 10 minutes ago or 5 minutes ago. But why do you think they're lids? Ethanol has a boiling point at 74, I think, or 76, and is highly volatile. One of the things you know about ethanol, highly volatile. So I think using a lid is a good idea. We need the lid to hang the, not necessarily, I've seen them, that just sounds wrong. I've seen them use pencil to hold it in place, right? I think ethanol is volatile, that's why they have a lid. Which diagram A, B, C, D? I like D, I think. D is the one? Yeah, D. Describe 2 mistakes made by, so the big mistake I think is this one, right? And what would that do? Mistake 1 is the dye is, I have to change my color. Dye is submerged in ethanol. And why is that bad? Instead of going up, the dye will just, oh, explanation, they're asking for it. The dye will dissolve in, ethanol or pigment or chemical. Right? They're asking for Miral, they're asking for this particular experiment. So I don't think they've stated if it's, oh, there is ink. I didn't even notice that. I like that one a lot more. Yeah. So you can say ethanol might evaporate. Oops. Ethanol might evaporate and you have to use a lid. I like the dye one more. Oh, sorry, the ink one more. Mistake is, what's this called? Baseline is drawn in ink. What's a good color? And the reason, explanation is, why is this a mistake, is because the ink will also dissolve. Dissolve and ruin your. Can you tell which topics would prepare me for my O-levels ATP? Paper 2 has been cancelled. So, you know, identification of ions is a major one, just your usual moles and titration. And energetics, rate of reaction, would be 2, 3. What else comes to mind? Not impure. The ink mixes with the dyes. Not impure, making it hard to see. So it will mix up. You can also say it will mix with the dye, and yeah. Mistake 3, if you're looking for it, lid. Can we see another mistake? Chromatography paper, that's the same. Depth of ethanol, that's just changing because the, or you can also say baseline is in ethanol, right? And that would ruin, didn't we say that? Dye is submerged, okay, baseline is below, okay, that we said that. Spot of pigment, yeah, I think that's it, three mistakes. Let's move on. Chromatography often uses water in the beaker. Suggest why ethanol is used instead of the water. Why do you guys think? So ethanol is probably dissolving all the dyes, and water probably doesn't dissolve all the dyes. All the dyes or the pigments being used are not all soluble in water. So what's the best way to answer this? I guess we can just say the pigments dissolve in ethanol. I love it, ethanol, so cool. Other classes we had except for, no, only past papers for now. We will have 1 or 2 classes related to salt analysis. I keep saying salt analysis because in A-level this is called salt analysis. Identification of ions. We'll do that in detail. And is there anything else left? Chromatography is done, right? Have we missed anything? You guys let me know. I think 1 or 2, yeah, okay, I have to open that sheet. I think very minute things are left. You know, minute and minute, they mean the same thing. Abdul Ghani, ethanol has low BP, but what does that do? Oh, oh, I wasn't reading the question. What property of ethanol makes it hazardous in the laboratory? If ethanol is less volatile, it's not poisonous or anything. So their low boiling point doesn't really matter. But ethanol is a fuel. What's bad with fuels if you have petrol lying around? Why is that bad? It's extremely, let's get decorative. Ethanol is extremely what? Maybe not extremely. Flammable. Did you guys know flammable and inflammable mean the same thing? Thank you, British people. And what can we do? Keep away from open flame. From open flame. Easy. Did you guys know inflammable and flammable mean the same thing? I think there's another word that means the same thing. What is it? Like the no, ethanol being volatile is not dangerous at all. Other liquids are volatile. Water is technically kind of volatile. It's not bad for you. The diagram shows the result for 3 unknown pigments, W, X, and Y. How many pigments are there in grass? Please, whenever you have a question like this, just do this. Do me a favor and just do this. Or do yourself a favor. Now answer me. How many pigments are there? Explain. Oh, in grass. Oh, okay. I was gonna... Okay, what's grass is? Green, so we'll use green. 3, because there are 3 dots. Let's go for grass, just to be specific. Which pigment is in all 3 plants? I wonder which pigment. See, when you do this, it makes life so much easier. Mistake. Calculate the RF value for pigment W. I cannot do that, but what you'll do is distance traveled by the solvent, sorry, by the dye, divided that by distance traveled by the solvent, right? Multiply that by, or no, you don't multiply it by anything. And 2 marks, I wonder why that is. Probably they're looking for the formula. Distance traveled by dye, dist traveled by solution. And I think it's 0.7 or 0.6. Let me just erase this. What does it look like? This looks like 60%. It could be 65, I don't know. 0.6. Right? Now, you know how to do this, right? Whatever this length is, measure it with a ruler, and this with a ruler. Distance traveled by the dye, traveled by the solution. Which of the plants contain W? W is here, the green one. Grass and spinach. Keeping true to our plant-themed answering session. Grass and spinach. I was just looking this, checking the spelling for spinach. ठीक है. ठीक. What do we have after this? Oh, okay. One more question. We can do this. 9:59. Can we do this real quick? I will do this real quick. Amna Khan. 2 says 2. Ooh, 3. Oh, okay. You're answering one of the older questions. A student investigates the reactivity series by putting pieces of metal in aqueous solutions. The table shows the experiments. Okay, complete the table. So you put copper in magnesium sulfate. What's going to happen? The more reactive metal, it's a displacement reaction. Can you imagine how tiny displacement reactions are? And I think that shows up a lot. Thermometric titration. Thermometric, probably not. Like, that's not even in our syllabus in any of them. So, no. Table shows experiments. Okay, displacement reactions, as I was saying, they show up a lot. And it's very easy. It's just the reactivity series. Anyway, so more reactive displaces the less reactive one. Is copper more reactive than magnesium? No, copper is very less reactive. That's not how you say it. Can I just say, I want to figure out what to say over here, but I'll cheat from here. Like, okay, no change, they want no change, they're saying no change, I'll say no change. Any change? No change. What change? No change. Okay, but let's read the other ones. Copper and iron, no change. Okay. Oh, wait, what? Oh yeah, iron is more reactive than copper. I was reading it ulta. Magnesium with copper, it will change, and what will happen? Red-brown solid form. So copper shows as a red-brown solid over here because it's hard to see. Okay, fine. Magnesium and zinc sulfate, silver gray solid form because zinc is produced. Okay. Magnesium and iron. What's gonna happen? Iron will be produced. What do you guys think? What do you guys think I'll write here? Iron is also being produced here, and they say gray-black solid form. I'll also say gray-black solid formed. Okay. Red-brown solid formed. Red-brown solid formed. And they're not talking about iron. Some might be confused. Hey, isn't red-brown iron? They're not talking about iron. They're not talking about ions. These are, not ions. Oh well. Sorry. Red-brown is formed. Red-brown is also formed here. What was in the solution? Copper sulfate was in the solution. So of course, right now iron is reacting with copper sulfate solution. And we'll make it blue because copper sulfate is blue. Copper to sulfate. Okay, and I think we're done. Complete the table. I already know the answer because I know my reactivity series. But over here, no change because copper is less reactive. Copper is less reactive than magnesium. Copper is also less reactive than iron. Magnesium is more reactive, but we already knew that. That's not giving us anything. Magnesium is more reactive than zinc. And what? Magnesium is more reactive than iron. Sure, okay. Yeah, I think if you're working with this, why is this confusing me now? Iron is more reactive. So copper is at the bottom, we know that. So let's write copper at the bottom. Okay. I'm just doing this in case we don't know. I'm trying to work it out. So we saw copper is just not reacting anywhere, right? So that's it. We're done. And I think zinc is second. Wait. No, zinc would be third. Zinc and magnesium are... Sorry, where's magnesium? Magnesium with iron. Magnesium and zinc are both displacing iron. So they're both more reactive than iron. So iron has to be right before copper because there are 4 metals present. Right? Now the fight is between magnesium and zinc. Where? Okay, there we go. No change. So magnesium is more reactive than zinc. So Mg comes on top. Yay, winner. And we have zinc on second. I can't believe we did one paper. Okay, magnesium, zinc, iron, copper. We did skip one question. That was 5 marks. TK, is that clear? Did you guys, oh, it's 10:05. Did you guys enjoy this? Okay, I'm just gonna end it because I'll probably use it. Magnesium is most reactive? Yes, magnesium is most reactive. Let me know how the feedback, let me know your feedback. Did you guys enjoy this? Was I going too fast? Should I explain it more? I think salt analysis will have a separate class because you can't explain salt analysis. You can only practice it doing questions. I think we should do that. But until then, I'll see you guys tomorrow. Bye-bye, guys. Take care. Take care. See ya.